June 1925. The air inside the Harvard College Observatory is thick with the scent of old paper, photographic chemicals, and chalk dust. It's a masculine space, a sanctuary of cosmic inquiry where deep voices murmur over glass plates etched with the ghosts of distant suns. In this hallowed hall, a 25-year-old doctoral student named Cecilia Payne moves with a quiet intensity that belies the intellectual firestorm she is about to unleash. She has just submitted her PhD thesis, a document that represents years of painstaking labor, hunched over a plate measuring machine, deciphering the silent language of starlight. This isn't just a graduation requirement for her. It is the culmination of a journey that began across an ocean, fleeing the suffocating intellectual climate of Cambridge, England, where women were permitted to learn but not to graduate, to discover but not to be credited. She had come to Harvard, to the supposed vanguard of astronomical research, seeking a place where her mind could finally be measured on its own merits. Her thesis, titled Subatomic Matter, sits on the desk of the most powerful man in American astronomy, Professor Henry Norris Russell. The document in his hands is more than an academic exercise. It is a cosmic Rosetta Stone. For decades, astronomers had operated under a comfortable geocentric assumption that the stars, including our own sun, were fundamentally made of the same stuff as the Earth. They saw the prominent spectral lines of iron, calcium, and sodium in starlight and concluded, logically, that stars were giant, glowing rocks. This was the orthodoxy, the bedrock of astrophysics, a truth so self-evident it was rarely questioned. But Cecilia Payne had questioned it. She had armed herself with a revolutionary new tool not widely understood by the old guard of astronomy, quantum mechanics. Specifically, she wielded the Saha ionization equation, a complex formula from Indian physicist Meghnad Saha that connected the spectral lines of an element to the temperature and pressure of its environment. She realized her predecessors were reading the stars all wrong. They were like travelers in a foreign land who could recognize letters but couldn't understand the grammar. Payne didn't just see the letters, she understood the language. Her findings? After analyzing thousands upon thousands of stellar spectra, meticulously cataloged by Annie Jump Cannon and the unheralded Harvard computers, Payne's calculations pointed to a conclusion so radical, so completely contrary to established belief that it felt like heresy. The data was unequivocal. Stars were not like the Earth at all. They were monstrous spheres composed almost entirely of the two lightest, simplest elements in existence, hydrogen and helium. The heavier elements that so dominated their spectra, the iron, the calcium, the silicon, were present only in trace amounts, mere whispers in a cosmic roar of hydrogen. This discovery didn't just tweak the existing model, it shattered it. It meant that hydrogen was, by an astronomical margin, the most abundant building block of the entire universe. It was a truth that would redefine humanity's understanding of its place in the cosmos, explaining the very engine of the stars and the origin of all matter. This is the revelation that now sits before Professor Russell. He is a titan of the field, a man whose pronouncements carry the weight of scientific law. His approval is the gate through which all aspiring astronomers must pass. Payne waits, her future hanging on his verdict. The meeting, when it comes, is not a celebration of her genius. It is an intellectual execution. We can imagine the scene from her own accounts. Russell, peering over his spectacles, his voice a mixture of paternalistic condescension and unshakable authority. He doesn't dispute her methods. He doesn't find a flaw in her application of Saha's difficult equation. He simply rejects her conclusion. Why? Because it cannot be so. It contradicts everything he and every other leading astronomer believes to be true. He tells her the vast overabundance of hydrogen she has calculated is clearly impossible. The words hang in the air heavy and final. He then delivers the career-defining advice, an instruction cloaked as a suggestion. She must remove this central earth-shattering conclusion from her thesis. To publish it would be to brand herself as a fool, to fly in the face of accepted wisdom and risk the ridicule of the entire scientific community. He is offering her a path to survival, a way to secure her degree and a modest place in the world of science. But the price is the truth. The price is her discovery. The system, embodied in this one man, was telling her that her evidence did not matter. His authority did. Who dares to challenge such an established order, and at what crushing personal and professional cost? Following that devastating dismissal, Cecilia Payne was faced with an impossible choice: capitulate and erase her discovery, or defy the most powerful man in her field and risk professional annihilation. She chose a third path, a heartbreaking compromise born of intellectual integrity and pragmatic survival. She did not remove her conclusions from her thesis. Instead, she buried her life's work under a veneer of self-deprecation, a qualifier forced upon her by the very authority figure meant to be her guide. In the final publication of 1925, after pages of brilliant, meticulous deduction, she included a sentence that stands today as a monument to institutional intimidation. Referring to her own calculated stellar compositions, she wrote that the extreme abundance of hydrogen and helium was almost certainly not real. It was a scientific retraction made under duress, a quiet act of protest that allowed the truth to be published even if it was immediately disavowed by its own author. The book was printed, a masterpiece of astrophysics containing the keys to the universe. But its most important door was marked with a sign that read, "Do not enter." The evidence she presented was, to anyone who understood the new physics, irrefutable. Her meticulous analysis of stellar spectra was a masterclass in scientific reasoning. For years, astronomers had been puzzled by what they called the hydrogen anomaly. In the spectra of very hot stars, the absorption lines for hydrogen were incredibly strong, while in cooler stars like our Sun, they were relatively weak. This led to the logical but incorrect assumption that hot stars had more hydrogen than cool ones. Payne, using the Saha equation, proved this was a profound misunderstanding of atomic physics. She showed that in the Sun's atmosphere, at a searing 6,000 degrees Celsius, most hydrogen atoms are ionized. Their electrons are stripped away, making them incapable of absorbing light at their characteristic frequencies. The hydrogen is there, in overwhelming abundance, but it's largely invisible. Conversely, the tiny traces of heavier elements like calcium are at a perfect temperature to absorb light with maximum efficiency, creating deceptively strong spectral lines. It was a brilliant, counterintuitive solution, akin to realizing a crowded stadium seems empty because most people are sitting in the shade. She had solved the anomaly, and in doing so, revealed the true nature of the stars. Yet, the wider scientific community, with a few notable exceptions, remained blind. They were swayed by the immense authority of Henry Norris Russell. If he declared it impossible, then impossible it must be. Her thesis was praised for its methodical rigor, for its detailed work on stellar temperatures, but its central revolutionary conclusion was almost universally ignored. It was a truth hidden in plain sight, a paradigm shift that the old paradigm simply refused to acknowledge. For years, Payne continued her work at Harvard, but not as a professor. Despite possessing what astronomer Otto Struve would later call the most brilliant PhD thesis ever written in astronomy, she was given the title of technical assistant to the director Harlow Shapley. Her salary was paid from a fund for laboratory equipment. She was a ghost in the machine she had helped to build, teaching courses that were not listed in the official catalog, mentoring students who would go on to greater acclaim, and watching as men with far less significant contributions were promoted above her. Then, in 1929, 4 years after Payne had been forced to disavow her own work, Russell published a paper in the Annals of the day. In it, he arrived at a startling new conclusion. The sun he had discovered was composed predominantly of hydrogen. He had reached this conclusion using different methods, but the result was identical to the one Payne had presented 4 years prior. The truth had become undeniable, and now that it was being presented by a man of unimpeachable authority, the world was ready to listen. And what of Cecilia Payne, the woman who had first scaled this intellectual peak? In his landmark paper, Russell acknowledged her foundational work in a single passing sentence, a footnote in the history he was now claiming to write. He briefly credited her 1925 thesis for showing the high abundance of hydrogen, but framed it as an early, flawed attempt that he had now corrected and confirmed. It was a masterful act of academic appropriation. He had not stolen her data, but he had stolen her priority, her discovery, her place in history. The system had not only suppressed her truth, it had waited until it could be safely laundered through a male authority figure. Whose name, then, would history remember for unlocking the universe's most fundamental building blocks? Building on that belated, minimal acknowledgement, the name history chose to remember for decades was unequivocally Henry Norris Russell. Textbooks printed in the 1950s, 60s, and 70s would lionize him as the man who discovered the composition of the stars, while Cecilia Payne Gapashkin was either relegated to a footnote herself or omitted entirely. The narrative was set. A great man of science had corrected a puzzling anomaly, bringing clarity to the cosmos. The quiet, persistent work of the woman who had handed him the answer years earlier was a detail deemed unworthy of history's attention. The system hadn't just failed to recognize her, it had actively written her out, replacing her name with that of the very man who first suppressed her discovery. But a truth as fundamental as the composition of the universe cannot be erased forever. The legacy of her work was too immense, its ripples too profound to be contained. Her thesis, now widely recognized by historians and scientists as one of the most brilliant PhDs in astronomy history, did more than just correct a single fact. It fundamentally shifted our understanding of the cosmos and laid the groundwork for nearly every major astronomical breakthrough of the 20th century. Knowing that the universe is 99% hydrogen and helium is the starting point for all of modern astrophysics. It explains the engine of the stars themselves, nuclear fusion, the process of forging hydrogen into helium which powers every sun in the sky. It is the cornerstone of theories of stellar evolution, allowing us to map the life cycles of stars from their birth in vast hydrogen clouds to their deaths as white dwarfs or supernovae. Her discovery provided the first powerful piece of observational evidence for what would become the Big Bang theory, which predicted a primordial universe made of almost nothing but hydrogen and helium. Every time we analyze the chemical evolution of a galaxy or trace the origins of the carbon in our bodies to the heart of a dying star, we are standing on the bedrock that Cecilia Payne laid down in 1925. The reckoning came slowly, fueled by a new generation of historians of science who were no longer content to accept the great man narrative of the past. Scholars, many of them women, began digging through the archives, re-examining the primary sources, and exposing the pervasive gender bias that had shaped the historical record. They read Payne's thesis. They read Russell's papers. They saw the timeline, the dismissal, the footnote, the appropriation. The evidence was as clear as the spectral lines she had once studied. Slowly, painstakingly, the story began to change. New textbooks were written, documentaries were produced. Her name, once a whisper, began to be spoken with the reverence it deserved. At Harvard, her own journey was one of incredible perseverance. Despite the initial setbacks, she stayed, conducting research for decades in a low-status, underpaid position. It was not until 1956, more than 30 years after her groundbreaking thesis, that she was finally made a full professor and the first woman to chair a department at Harvard. She had outlasted the system that tried to sideline her. Her story is a stark reminder that science is not a purely objective pursuit of truth. It is a human endeavor, susceptible to all the biases, power dynamics, and injustices of the society in which it operates. Cecilia Payne's discovery was not impossible. The system she was in was impossibly biased. Her voice was not wrong. It was simply not the right gender. Credit was not given, it was taken. Her restoration to her rightful place in the astronomical pantheon is a victory for the historical record, but it leaves us with an unsettling and vital question. We have found this lost star in the firmament of science, but her story forces us to look back into the darkness. The question remains, how many other fundamental truths whispered by marginalized voices were silenced or stolen before they could truly shine?